Hi everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at another group on the periodic table called the noble gases. To start us off though, what I'd like you to do is have a go answering these three questions in your book based around our previous work on this topic. Okay, let's double check those answers then. So for question 1, our word equation, remember it has to be the full words here, no symbols. We should have chlorine plus lithium iodide makes lithium chloride plus iodine. Now if you also wrote the INE at the end of lithium chloride, so you wrote it as lithium chlorine, then that is also wrong, I'm afraid. So where it's joined onto the lithium, it must end IDE. Where it's on its own as the halogen, it must end INE. For question 2, yes, we would expect a reaction for 1 mark, and the reason for that is because iodine is more reactive than astatine for our second mark. Then finally, we would expect to see a reaction with our fluorine because it's more reactive than chlorine. So add up your score and give yourself a mark out of 4. What I'd like you to do then is see if you can finish off these points, writing them in your books. So you can see we've got a few blank spaces there, and remember you are allowed to use a periodic table. So write down the first sentence, filling in the blanks, and then hopefully the list of the elements, filling in their names. So our first sentence there, group 0 of the periodic table are also known as the noble gases. Now I'm hoping the title of today's lesson might have given you a little bit of a hint about that one. And in the names of the gases we've got He is helium, Ne neon, Ar is argon, Kr is krypton, Xe is xenon, and Rn is radon. So tick any of those you got right, anything you didn't, obviously make sure you've written the corrections in. So when we think about group 0 then, we refer to them as the noble gases. What I'd like you to do is see if you can write down a suggestion in your books as to why we call them the noble gases. So I'll just give you about a minute and a half to do that. The reason we call group 0 the noble gases is because they're actually really unreactive. So they don't take part in many chemical reactions at all. And what you can see in the little cartoon on the right hand side there is we've redrawn those squares on the periodic table to represent that noble class in the past. Now the noble class were the ones that kind of just sat around a lot and didn't really do anything. So they had all their servants to do the jobs for them and they just were there. Kind of like the noble gases. They're around but they don't really get involved in things. So the reason we call them noble gases is because they are unreactive. So they're not taking part in many chemical reactions. Make sure you've got those 2 points written down for me in your books. With these 2 sentences, they're about the properties of the noble gases, and you'll see there are a selection of words in brackets. Now don't write them all down. what I want you to do is select the one correct word from each of the selections within the brackets to finish those sentences. Let's make sure we got those right then. So our first one, they are non-metals. Tick it if you got it right. And the reason we know they're non-metals is because group 0 is the column on the far right hand side. And hopefully we remember that the right hand side of the periodic table are the non-metals, the left hand side are the metals. They're all gas at room temperature, and I hope that you got that from their name, the noble gases. This isn't some kind of a weird sciencey joke, it's just stating a fact. They are all gases. So tick that one if you got it right and give yourself a score out of 2. Now, one of the things that we did in our earlier chemistry topic was drawing electronic configurations. So what I'd like you to do is draw the electronic configurations for helium, neon and argon, then see what you notice about their outer shells. Once you've spotted whatever pattern there may be, I want you to try to use that to explain their reactivity. So 3 electronic configurations first of all, what do we notice about the outer shells, and then how can we explain the reactivity using that information. Okay, so let's start off by drawing their electronic configurations. So our first one then, helium, that has a total of 2 electrons because its atomic number is 2. So when we draw its electronic configuration, both of those electrons go on the first shell. The second one, neon, that's got 10 electrons. So we start with our first 2 on the innermost shell, but it can only hold a maximum of 2. So we then need our second shell, and we're going to find the next 8. There we go. So that's 2.8. So that's the 10 electrons there. And then we've got argon. So the first 2 electrons for argon go on the first shell. Then we get the next 8 on the second shell. And then we have a third shell, which again has the 8 to take it up to its 18. So that one is 2, 8, 8. Now, hopefully what we remember are the rules for the shells. If you remember, the first shell can hold a maximum of 2, the second shell can hold a maximum of 8, the third shell can hold a maximum of 8 as well. So when we're looking at these, what we notice is if we look at the last number in each case, then it is the same as the maximum number of electrons. So what we can see in terms of our pattern is that they all have full outer shells. So if you got that, give yourself a mark for that bit. And incidentally, each one of these is worth 1 mark each up here. So you get 1 mark for the actual drawing, another mark for writing the configuration. Then we've got our pattern, and the last thing we need to do is then talk about how that impacts their reactivity. So because they've all got full outer shells, then this makes them unreactive. Because if they've actually got a full outer shell, if they've got a full outer shell, then what we find is that they're not going to easily gain or lose electrons. So what we find is they're unreactive as a result of that. And there's your answers to that question. So add up your scores and give yourself a mark out of 8. There's a really important word that we associate with the noble gases, which is the word monatomic. So see if you can write down a definition for what you think monatomic actually means. Monatomic, if we break that word down to mon, or we can add the extra O in there to mono, which means 1, and atomic, atom. So what we're talking about here with a monatomic structure is a single atom. And those single atoms have very weak forces of attraction between them. So write that definition for monatomic down for me. Obviously, if you didn't get it already, if you did, then just give yourself a lovely tick. And then see if you can explain what impact this would have on their boiling points. So what we find is that as we go down group 0, so start at the top, work your way down, then the attractive forces between the atoms get stronger. And the reason for that is we're having more shells, so the atoms are getting larger. So larger atoms have stronger forces of attraction between them. Because they've got a stronger force of attraction between those individual atoms, then the boiling point is going to increase, because it takes more energy to overcome those forces between them. Another pattern we should note is that their density also increases. So make sure you've got those points written down about the patterns that we see within group 0. Final thing for today then are your plenary questions. So those who with target grades up to grade 5, the 2 columns on the left. Those who with target grades over a grade 5, it's the 2 columns on the right. I'm going to leave these up for just under 3 minutes today, so if you need longer, obviously hit pause, take as long as you need to answer them in your books.